and was one of the Viterbi India Fellows in summer 2015. Over to you, Professor.
Okay, thank you, Shishma, for the kind introduction, and thank you to the CNI team for having me here. So, yeah, as the title suggests, I will be presenting some of my research works in. Okay, I will be presenting some of my research works in enabling AI ML at the edge. So, developing some efficient and robust solutions, and some of these works were presented in different places, so I would like to mention the slide credits to Professor Salman Avestimar. He was my PhD advisor at USC, and then Sunwoo Lee at Inha University, and Dr. UNU at Meta, and Dr. Rami Ali at Samsung. Okay. So I guess I don't need to motivate much that big data is very important. It's being generated at a massive scale at the edge, and especially emerging 6G and beyond client edge devices. They are capable of a lot of sensing, collecting, and processing. They are capable of doing all these things increasingly, more and more capable. So it's not wrong to say that data is kind of born at the edge, and privacy, latency, bandwidth, and many other concerns such as scalability, it is kind of driving the local processing of information. So if I want to unlock my phone, I would like all the computation to happen on the phone. It shouldn't connect with internet. Suddenly, if the connection breaks, then I lose access to my phone. And although these concerns are there, but at the same time, the compute, communication, and sensing as well as storage capabilities, they are also becoming richer and richer in our current devices. For example, our phones are having more and more storage, more and more computation capabilities. So all of these things are kind of suited for on-device AI and ML, especially personalized healthcare, maybe some banking applications. Nowadays, a lot of chat GPT like solutions. So one key question arises, how to enable AI and ML applications at such a massive scale. And there are many industries that are working on such problems. For example, Flower is focused on federated learning libraries, and then Google is there, Microsoft is there, and so on. And this is FedML, which was started in my PhD group, co-founded by my PhD advisor and another PhD colleague, and it has transformed into many other things. Okay, so just some basic fundamentals. So this is machine learning. We have a data set, and there this is specifically supervised machine learning. So there are all these different classes. The idea is to capture all this information into a machine learning model. And using this machine learning model, I should be able to classify data points which come later. Okay, so the key idea in a nutshell is that I want to train a machine learning model which minimizes some loss function over the data set. And this is some regularizer. And typically this is done through some iterative updates. For example, gradient descents, SGD could be there, and so on. So the key component in this which I want to highlight is this gradient. So this gradient is the sum of gradients. This gradient over data set is sum of the gradients over the entire data set. Okay, so keeping this in mind, so what is distributed machine learning? Because I mean, one motivation for distributed machine learning is that I want to uh, train large models on large data sets. I cannot do it in one place, so I would like for this to happen in a distributed manner. And there are various ways to distribute data as well as model. You can have model partitioning, data partitioning, and so on. But just to kind of highlight what is distributed learning, I am focusing on data partition. So this full data set is there. I distribute it to three different clients, three different servers, D1, D2, and D3. And then each server is going to do a gradient computation over its local, over this assigned data set. And these partial gradients are kind of shared with the server, master server, and then the sum is obtained from these partial gradients. And then the server, the master server can update the global model and in the next iteration, the updated model can be shared again with the worker servers. Okay, so this is how distributed machine learning happens in a quick overview. So now what is federated learning? Many of us are now familiar with this. So the idea in federated learning is that the data cannot be controlled by one central entity. It is now available at different participating clients. And these could be our own edge devices like mobile phones, laptops, and so on, some drones doing some visual analysis on some areas and so on. So now the goal is that I still want to be able to train some machine learning model over these distributed data sets, but the server doesn't have access to them directly. And in this process, maybe all these clients want to participate, but they don't want to share their data. But in some collaborative way, maybe they are trying to learn some individual functions, like this client may be trying to learn some personalized model, and it should have uh, something related to some information from the remaining clients. And similarly, other clients also, they might be trying to train different personalized models over the entire federated data set. So overall, this is the bigger picture. So I kind of work in two key edge AI ML paradigms. So in the first one, it is simply like user cloud setting. So the idea is that I have some query, I want to get some output out for my query. And this requires some large computational facility. I don't have that facility on my local device, so I have to interact with the cloud. So for example, I'm doing some chatting with Gemini or ChatGPT. So I'm kind of giving a lot of information from my side in order to get some utility out of ChatGPT. So you can see in this process, I am sharing a lot of information with OpenAI. Now, it may happen that you may be interacting with ChatGPT and you might be sharing a lot of private information, maybe your health information, your maybe family information and so on. And if there is a leakage, and once in a while we keep hearing about user data leakage in banks, and also at some point OpenAI, it had some bug in because it was using some open source code. A lot of data got leaked. A lot of these chats got leaked. So there's a lot of privacy concern, but then I cannot run ChatGPT like models efficiently on my own device. So what should I do? So there are all these trade-offs that I try to explore. And another one is the federated learning setting. This is kind of another, this just a more detailed description. The idea is each client is having its own data set, and then each client is going to send a model which is updated only on its local data set. These updated models are shared with the server, and then the server is simply updating the global model from xt to xt plus 1 by combining all these locally updated models. So that's federated learning in a nutshell. Now in all these settings, these edge ML, AI ML settings, there are a lot of concerns and issues when one tries to deploy them in practice. For example, there are a lot of resource heterogeneity. My mobile phone will be very different from my own laptop. And across users, across maybe different institutions, there may be very large differences in compute capabilities. So resource heterogeneity is a big issue. And also some devices may be very severely resource constrained as well. So this is a very significant issue. And then there are all these errors and malicious clients that can come into the system. For example, in this setting, this edge setting, the client can query anything, right? As a user, I can type anything. Now there are many proper things in place so that if I query something wrong, they do not answer. But in the beginning, it was not the case. So people were able to attack these chat bots, and they were able to extract a lot of information. So malicious clients is always a problem in edge machine learning and AI problems. And then although you may think that if I don't share my data, I will just share my model and I will be safe, but that is not true. So even from models like machine learning models, especially deep neural networks, you can extract the training data out of the model itself using some attacks. So one of them is model inversion attacks, and there are also membership inference attacks by which you can predict, by which you can find whether your own training data was used or not. So all these issues are also there. So yeah, I kind of work in different problems trying to address one or more of these issues in each of those problems. So the question that I had in the previous slide, how to do these things at scale, it kind of becomes more refined. So the question now becomes how to enable efficient, robust, and trustworthy solutions for edge AI ML. Okay. Now I'll go into one of the research problems that we addressed in our group. So training of large models at the edge. So as the title suggests, so I'm trying to train a model in a federated learning paradigm, and I want to train a large model. So this server wants to train a large model, but then the issue is that uh, there are many challenges, like this small device, it cannot load, let's say, the model itself. So how do I do federated learning? Because remember, in federated learning, the one of the steps is that each client should update the model locally. So the local update cannot happen efficiently if I have limited resources in place. So how to efficiently and effectively train large deep neural networks over resource constrained edge devices? So this is the question. And you might think that, okay, in federated learning, let's say this device is very small, I will not utilize its data in the federated learning process. But then it may cause severe degradation in accuracy, because some of the clients might be bringing very rich data sets. And on top of that, it may happen that certain demographies may not have access to good computational infrastructure. So if you ignore those clients, then you will be biased against those demographics. So, and one example is maybe industries have so much of GPU infrastructure, thousands and thousands of GPUs they can use to simply pre-train models. But in academic institutions, it might be difficult. So yeah, so then this issue, it will be unfair to exclude clients due to limited resources. And this is one illustration. So I have included 3 client devices, and I'm just denoting what the storage values are, the internal storage. So already we see that in terms of internal storage, there is so much heterogeneity, right? So the conventional assumption which used to be there in federated learning, that the clients are homogeneous and they are powerful, it does not hold. And just for illustration purpose, imagine that this rectangular box is the memory of this mobile phone, and it is just enough to train this neural network. So already I can see that if the model is relatively this large, that it is just fitting in the memory space of this phone. Maybe other phones are having smaller memories, maybe proportional to the internal storage. So I can already see I cannot train such a large model in the same amount of time, essentially, in these smaller devices. So what happens when model is so large? Small and weak devices cannot even hold the entire model in their memory space. Then how do I do federated learning? Okay. So goal is to enable weak client participation in FL, and we consider weak clients that cannot effectively train the full model on its own due to maybe limited memory, to weak compute power, and we want to utilize the distributed data in the real world. So we have to make all available devices participate in the training. Okay. So at the heart of what I'm going to propose and what other works have done previously, before our work, is something called submodel training. And the idea in submodel training is something like this. So here I have, just for illustration purpose, this is a fully connected neural network. These are the 3 inputs and these are the 2 outputs. All we need to do is that we need to update these model parameters. So submodel training just focus on these model parameters which are inside this dotted box. So submodel training simply means that each client is only assigned a subset of model parameters. So for this client, this smaller neural network is enough. So it is only going to update these parameters using local machine learning. And similarly, the other two clients are also assigned a subset of the entire model. So we can see that each client is only training a submodel. So after local training, what will happen? These updated parameters will be shared with the server. It will aggregate the information depending on who trained what parameter. For example, this red one and this red one are trained in the first two clients. So it is only updated in the first two clients. So in the new model, this value will be maybe a simple average of those two updated values. Correct, correct. So that problem is there in general in federated learning also, right? Mm-hmm. Yes, right, right. So that's why I mean the next question is how to create a good submodel. Yeah, that's a big problem. Yeah. So yes, yes, yeah. So and actually the first few works that came, they kind of did some heuristics on this, and then we developed something which I'll discuss. Okay. Uh, So yeah, so in the first work, and this was kind of a very important step. So the same work kind of got published in both NeurIPS and ICLR in 2021. Uh, so the idea was this. So in each layer, just allocate a subset of parameters. For example, for this client, these black colored parameters are not assigned. This is just for illustration purpose. So only these colored parameters are assigned. So the idea is that in this first layer, only this parameter is assigned. Second layer, only this. And third layer, only this. And in the other client, which is more powerful than this weakest client, uh, it will have like a larger subset of parameters. So in this layer, the first parameter as well as the second parameter. And similarly, in this layer, this one is included and additional two parameters are there. So what it did was that it just proposed an increasing subset allocation. And we can see it's a heuristic here, right? But at least it improved the performance, it allowed heterogeneous clients to participate and so on. So, and then this is also something you can relate to dropout. So dropout in neural networks, it was one of the revolutionary techniques. It improved performance, generalization performance, and so on. So this is kind of doing dropout on model parameters. So, okay. So now the next work, which kind of came and said that, okay, why are you dropping in original parameter space? We should do something different because there is no notion of the importance of each parameter, right? It's just that you select a subset, and then in the next client you are selecting a larger subset, but there's no notion of importance. So what they did was that they selected each layer, and on each layer they did an SVD. So this weight parameter, let's say, is the fully connected layer, and then I have to multiply W times X and to get the output Y. So they did SVD, and SVD, we know this singular value is kind of denoting the importance of that principal component. So what they said that instead of dropping in the original parameter space, do a dropout in the principal domain. So if a client can only train one principal component, assign it the principal component corresponding to the largest singular value. So at least some notion of importance was developed. And similar idea extends to CNN. It's related to principal kernels and 1x1 depth, but similar idea is there. You have principal components corresponding to your neural network layer, and then you assign the top R, where R depends on your local capacity. Yes. Yes. So you train a factor model actually. You don't train the full model. It's
you want multiple devices, right? And then
Correct.
what do you do for it? You want to leave one of these top one or each R of them, or what are you going to do?
So here it's like this client will get top, let's say one principal component. So the model parameter now becomes UI and then VI transpose. So those are the parameters. It's the original matrix is not reconstructed. So it's just two vectors essentially, and those are updated.
Next device.
Next device is the top three, let's say.
But
Yeah.
you want to go basically one, then top two, then top three.
Yeah, depending on what the model size the client can.
What about the subsequent layers?
So in each layer you are going to do this.
So each layer you're gonna just pick one, 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 one. You're gonna do two, 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 three, three, or what?
Yeah. Like this SI, whatever the thing. So the actual training, what happens is you take this SI, you do a route, and then you absorb it into UI and VI. You update those on different clients. You reconstruct your matrix essentially after averaging UIs and VIs.
I'm also not getting this.
Oh, okay, okay. I see. It's just like from your SVD, you have to reconstruct your matrix.
That is actually much easy, right? Because you just need to know the coefficients. Yet you're training, right? And then you're sub-training and see you actually have different data on each of these devices.
Correct, correct.
So it's not clear how to add them. I cannot just use the coefficient of scale, you can combine them, right?
So coefficient is absorbed, like it's gone. So yeah, yeah.
Anyways,
Okay, okay, sure.
what you have done, maybe you'll understand it better.
Okay, so my work kind of builds on this, but okay, so uh, okay, so but there is a significant issue in this process. The idea of, so what I'm illustrating here is that there is this resonate 18 that I'm trying to train, and these are different blocks of parameters. So it's just that a set of model parameters. So what I'm denoting here is that how many principal components are required to give a good approximation of my block of parameters. So in the beginning of training, what it is showing is that almost 60 principal components are needed.
So when you say 60, you mean like in each layer 60?
So the thing is, in these blocks, actually there are 64 channels. Sorry, this is like 64 channels. So 64 original CNN channels. And what this says is that so when I do a decomposition, I will have 64 principal channels. So what this is showing is that to have a good approximation of your original kernel, you need almost 64. So you cannot do a low rank. It's not low rank essentially in the beginning. Yeah. Yeah. So and then this low rank structure is kind of gained over the training process. And even at the end of training, you need at least like 50% of the principal components. So now imagine if a client can only, so first of all, if the clients are very resource constrained from the beginning and you do this top 50%, let's say, from the beginning, then you are going to lose a lot of performance. And even in a more severe case, when client can train only 25% principal components, each client can train only 25% principal components, then what will happen is that even I don't even achieve, I won't be able to even achieve this, because at no point in time I will be training 50% kernels. So that's what was missing in this work. So in heavily resource constrained settings, I won't have a good approximation at any point of time. Fine. Okay. So how to design a good way of splitting and utilizing the weak lines is now the question. Actually, I can write also there if there are some more questions.
Why do you want to stick with CNN only? And you're like, okay, we can just go with mixture of expert type of model now.
So one step at a time, no?
Which will probably be more amenable to this kind of setup where you want to have, you want to combine multiple devices.
So make
Fundamentally, I'm saying why were we so, like hung up on doing, this?
CNN.
This, I'm not even sure what it means. Different layer, you're picking part of it.
Mm-hmm.
Yeah, go ahead.
I mean, mixture of experts is just on a neural network, right? So it's.
Mixture expert has good connotation, right? I mean, it is motivated by some other
Okay, so that now boils down to like in federated learning, how do you train mixture of experts?
Federal learning, I'm convinced, but
Oh, you are convinced?
I'm not convinced. No,
Okay.
it works out there. It doesn't work out here. There is no. You're saying if SVD is good, then my output is good. I'm not convinced that.
So here I'm saying that the output was not good for this work.
Yeah, but
So
I'm saying the way you're doing this submodel thing, right? It's not.
see, it's something like this. Some technology is completely missing, so you have to take some baby steps, right? So this is like a baby step where you are trying to do federated learning with.
I'm just saying that I'm not convinced this approach. Continue.
Oh, okay, okay. That we can discuss offline. Okay. So this was the hypothesis. So let's say my neural network has two layers, and this is the training timeline for two different clients. So here what we do is that we let each client train independently. So what I'm illustrating here is that how do these layers look at the end of training. So let's say at the end of training, I focus on layer 1, and this I'm denoting it in same color. So what I'm trying to show here is that at the end of training, two clients have kind of learned similar knowledge. But then in the final layer, the colors are very different because what we found was two clients have learned different knowledge. So here what we see is that maybe this was kind of our motivation. So if you have a weak client which cannot train all the layers in the neural network, maybe let it train the final side subset of layers. So the initial layers are kind of will be covered in the stronger clients as well. So what I mean is this. Oh, before that, so we had this observation in different settings. So this was like CFAR 10 and ResNet 20. And what I'm showing here is that what is SVCCA? So SVCCA is kind of denoting the similarity across clients in a nutshell. So more SVCCA, the higher the similarity. So what I'm showing here is that at the end of training, the first layer, it has a very high similarity across clients. And then the last layer, which is closer to the output, it has a much lower similarity, like 0.4. And this we also observed in IMDb and LSTM training. So embedding layer had a higher matrix values, yeah, like layers. Yeah. Correct. So yeah, like convolution layer 1 you take, and then you try to find the actual matrix, subtract, and then you find the norm and so on. So the input side layers, they learn similar data across independent clients. So this was our key observation, and based on this we proposed this method. So as I just mentioned, maybe for the weaker clients you can design a process where only the second layer is updated, and or maybe the output side subset layers are updated. And in this example I only have two neural network layers. So the way it will happen is that I'll take a forward pass at this client, weaker client, and with this forward pass it will obtain these activations, and then the first layer is dropped. And then I take these intermediate activations and treat it as the input, and then just do my normal machine learning process. So the second layer will be updated at the weak client, and only this contribution is going to be sent to the server side. So weak clients are only going to contribute to the output side subset of layers. Model was sent to the client.
That model is sent.
Yeah, right.
You do layer by layer, but you only update something else.
Mm-hmm.
There's still a lot of I/O, right? You have to get the layer, get the layer, get the layer.
Yeah, right, right. But the training is what is more computationally expensive. Forward inference typically.
Still you're not. So I thought you meant submodel that you're gonna store only the submodel. Model parameter. So right now you're evicting model parameters also every time, right? Because you don't have enough storage.
Yeah, because I need to have a fresh forward pass in these. Yeah, 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 yeah.
So, but if you had for your training only say on submodel, which is what you keep at all times, and
Right,
that's what
right.
I'll update, and then I don't care about the rest of the.
Yeah, so that's the second work. Yeah, yeah, that also we have. Here we are not saving in the downlink. And the forward pass, we are still have to kind of do a forward pass layer by layer until I get the right input in terms of activations, and then I update the remaining model.
What is the right input?
Right input is just that these activations, I just need to have these activations.
I mean, the layer which you want to update.
Which I want to update,
So
right.
you forward pass till you reach
Correct.
the layer which you want to update, and there you check what the update should be.
Correct, correct. Yeah. Okay. And this is kind of the overview of the embracing FL, which is our name to the method. So the strong client, they are going to update both the layers, and then the weak client is going to update only the second layer. Yeah. And then at the server side, these updated parameters will be averaged depending on who is contributing to what. Yeah, in this work we did simple linear combination. Yeah. I'm currently exploring other combinations, so we'll see. Okay. I know. That's a very valid question. But yeah. So this was something leap of faith. So it works, right? But that's the other thing we are exploring, because we can see like if you might want to give more weight to this client because it's only training the last layer, and yeah, right. That's also there. Yeah, correct. Yeah, so this is one experimental setting. So strong clients, it simply means all the model parameters are there, are trained at the strong clients. And I'm only focusing on strong and weak. So weak clients, only these output side layers are trained at the weak clients. 16% model parameters are trained. Yeah. Okay, and these are some results. So each row is denoting one federated learning setting. In the first row, I have only 16 strong clients, and this width reduction was the first method which I presented, where it was an increasing subset of model parameters, the heuristic one. And this is our embracing FL method. So with 16 strong clients, we have some performance, 60%. And as I go down the table, I'm adding more and more weak clients into my federated learning process. So as I add more weak clients, what it means, I'm adding more data points. And with increase in number of data points, I should see an increase in accuracy. So both width reduction and embracing FL, they increase in performance, but we see that we are able to capture this much more efficiently. So we have reached from like 60% to 77% in the setting where 16 strong clients are there and 112 weak clients are there. So this method definitely achieves something. Of course, we are exploring better ways to do it. So these results empirically show that embracing FL, they better utilize the weak clients than both hetero FL and the FIOD, both kind of did the same thing. Oh, yeah, something in the original model parameter. Yeah, sure.
There.
Uh-huh.
If you could, if the weak client could fully use the information available, what sort of a world?
Yeah, right. So I think it will go like 85% or something, if I remember correctly. Yeah, all clients 128, they are training full models. I think it was 85, something like that. No, not much. No, I didn't. That's a good question. So, I mean, there are many things that go into this. Even in federated learning, I don't remember if there is a linear improvement if you add more clients. And on top of that, we have all these non-linearities and then model partitioning. So we didn't have much intuition. Only intuition we had was the initial layers are kind of common across clients. So maybe just train the final.
Sorry, but my question was more towards what Naresh asked about, like, if all the weak, if there is no constraint on the weak clients as well, suppose they are all training the same model.
Okay.
In that case, would you expect linear?
That's a good question. I'll have to see it. Yeah, even with this from 60 to 85, whether it increases 1%, because it's also dependent on data set, right? So we here we actually did non-IID partitioning in the sense like some clients had more proportion for other classes. But now imagine in the setting where each client is IID data distribution. So there it won't be linear, at least not the same increase as in non-IID case, I think. Yeah. Okay. So so now this was the problem. Any other question till this point? So this was the problem that we addressed in the previous slides. So this we wanted to train a large model, and relatively large model, it cannot fit in other clients. Uh, so now I want to address more difficult problems. So fundamental limitation of all the prior works is that all prior works, including our embracing FL, they required at least one client to train the full model. All layers should be updated in at least a few clients. But then what will happen if none of these clients can train the full model? So this is something that, this was actually the problem that I started working on, and we couldn't solve it. Then we moved to the previous one. Then we came back to this problem. Okay, so what happens when all clients are weak? Can the server still train a large model? And yeah, I'll be giving some results which answer it in yes. So these were the two works, as I was mentioning. This has an increasing subset in original model parameter space. This in this one, each weight layer, each weight is kind of decomposed using SVD, and only top R are selected. But as I mentioned, and this is the relative performance of these two methods. So orth drop is where you drop parameters in the principal domain, and orig drop is where you drop parameters in the original model. So what we see is that, yeah, so you were asking all full models, right? So this is roughly 85% in that setting. So all full models, it's 85%. And then what I am doing on the x-axis is I'm selecting different settings where I am restricting what fraction of full model can be trained in each client. So it's homogeneous setting, but very heavily constrained. For example, in this 0.2x, each client can only train 20% of model parameters. So in this setting, these other methods, they kind of degrade significantly. From 85%, they have come down to like 70% in non-ID setting. And in the ID setting, they kind of go from 90 to 93% to 87%, 87, 88. And we also see that the orig drop, which was the most heuristic method, it has a lower performance compared to the orth drop, which was dropping things in the principal domain. So at least that orth drop method had an importance factor in that, so it is performing better. But then, yeah, can we do better? And why we want to do better was this, just to remind. What I had shown here was that in the beginning, we need almost all the principal components to be trained. So it's not low rank structure in the beginning. So this is what inspired our method. So what we do is we propose a probabilistic sampling approach. So the key idea that we proposed was something called dropout in the principal domain, but then we proposed a probability aspect into it. So how it works? The way it works is that original kernels are there. Then I do an SVD, right? In the previous method, SVD was done. After that, what they did was they only selected the top three. Let's say each client can only train 3 principal kernels for that layer. So they selected top 3, and the top 3 was assigned to all the clients. But then, as I showed in the other plot, we need almost all parameters in the beginning to be trained. So that's where we came in, and we said that maybe we should do a dropout type strategy in each SGD step. First is centralized setting, and then if results are fine, we should go to the federated setting. So what we did was, from these principal kernels in each SGD step, I should be sampling which kernels to update, and only update those. And next SGD step, I should do another sampling and so on. And then there was a probability factor, and this probability of sampling was kind of proportional in some sense to the singular values, which I'll show in the next slide. So what is happening in each SGD step, the more important kernels are getting updated more frequently, but at the same time, I'm providing a better coverage of the lower importance kernels as well. And this improves performance significantly. So before going into FL details, let me present this plot. So in centralized training, this upper line, the dotted line is the full model. So I'm just doing normal training, CFAR 10, VGG 11 on CFAR 10. And then this orange drop is that in each iteration, I only do the training of top, the top subset kind of thing. And in the yellow one is the orth drop method, where I drop things in the principal domain, and that is like we only train on the top R. And that R is kind of denoted by this 0.2x, 0.4x, 0.6x, 0.8x. And this is our method, the blue curve, where we say we should drop, in this 0.2x, let's say I will be training only 20% of principal components, but how to select that is our probability-based approach. So we already see that in centralized training, it worked very well. Now, based on this idea, we went back to FL and created submodels. Okay. So this was our probability-based strategy. So our probability function, we spent a lot of time, of course we knew it should be associated in some way to the singular value, but what a function we should use, we did a lot of search, even softmax and all, took us quite a few weeks. But in the end, this is a very basic fact, right? The Frobenius norm square is summation of sigma I square. So using that, we thought that maybe we should have this probability proportional to sigma I square. And that was working well. And in our experiments, this kappa was actually roughly 2.2, 2.3 based on hyperparameter tuning. But just 2 was also working well in our settings. So that's where the intuition part came in. So we do this probability-based sampling based on the value of these singular values, and in this sigma I to the power kappa, and then we normalize it. So how it works in FL? So in FL, remember, we need to create submodels in each round. In each communication round, I need to assign submodels. So in this I am showing how 2 submodels were created for this particular layer. So because of the sampling process, the P1 was very large. So maybe it got sampled, because of that, this top principal kernel was assigned to both clients. But then the other 2, they were not identical. So essentially, we are able to provide more coverage across clients when we create more and more submodels out of this process. So that's how in each communication round, we were able to provide a better coverage of all the principal kernels. And that's why it gave us better performance in federated learning, which I'll show next. Is it clear? So here we already see instead of 3, I'm covering 5. And with more clients, I'll be covering more and more of these principal kernels. Okay. There's also some memory aspect. Let me skip. Yeah, so we haven't provided any analysis. We was already with this, we haven't tried that yet. It would be interesting. But the thing is, with deep neural networks, many times we go into theory and it just doesn't match with actual CNNs or whatever. So, but yeah, it's an interesting direction.
You said probabilistic sampling. Every time you're gonna choose a different kernel, or you sample it one and then keep it.
In each communication round, we'll create a submodel once.
No, what I mean is, you're doing training now, right?
Correct.
So in training that I sample, say, kernel 1.
Yes.
Kernel 1.
For a particular client, yes.
Next time I'm gonna choose another kernel 3 because.
Yeah. Next time I do the sampling.
The previous kernel parameters.
No, so one important aspect. So we have to have some model aggregation, right? So in the aggregation, what will happen, all these principal components, so let's say kernel 1 got assigned to client 1 and client 2, so that will be averaged and the new kernel 1 has been obtained at server. And similarly, other principal kernels are also obtained. So now you have to reconstruct the original weight.
This is fine, but now I'm going to get a new kernel 3 set.
Yes.
Now this time I sample 3.
Yeah, so after that you decompose and then resample.
So, but then but I'm not going to keep kernel 1, I'm just going to keep, because maybe it's not going to be a combination of 1 and 3, right? It's just going to keep kernel 3, right?
Kernel.
Or I'm going to just add to my kernel whatever the new kernel 3 comes.
So for the client side is just these kernels which are assigned. So there's no
Replacement,
just replacements like a fresh model. So this also addresses this issue that different kernels are actually seeing now different data sets also across rounds. So it's really federated in that sense. Clients are also having different models. Principal components are also seeing different clients. So yeah, so based on this, yeah, so this I just mentioned. So I have to do fed average of all these kernels, and then I have to refresh by reconstructing the original weight and then do a decomposition again in the next. Okay. So empirical results, whether it works in practice. So this was the plot I was showing with respect to orth drop and orig drop, and this is the blue curve which we propose. And we see in the non-ID setting with full model, the performance was 85%. When we reach the heavily constrained setting where each client is only training 20% of model parameters, the performance drops significantly for the other methods like 70% and so on. For our method, it is still above 80. So we are really able to shine, especially in the non-ID setting. In the ID setting, other methods are still lower, but maybe you can argue that the drop is not that significant. But when the data becomes really heterogeneous, this becomes, yeah, we are really able to perform much better. Okay. Yeah, non-ID setting, there are different ways. So one way is that the data set inherently is non-ID. So when people were developing all these federated learning, they created data benchmark also. So for example, there is federated extended MNIST. The idea is that they ask different users to write characters, 1, 0 to 9, then alphabets in capital, alphabets in lower. So each user inherently is a non-ID client. So that's how they constructed. For existing data sets, you can create non-ID with respect to class proportions. In different clients, you can have different proportions of class. Okay. And these are like the overheads results. So some machine we took, and then for local training, it was taking for each communication round 37 seconds, let's say. The overhead for SVD was very small. So we did not do normal SVD. We used some fast SVD from some other prior work, and it really improved the SVD decomposition step. And aggregate time is also very small. And sub-model creation, like you do principal component, then you do sampling. This is also very small. And this is all in one machine. Now imagine server. Server has much more powerful resource. So maybe these things will decrease by a factor of 10 or 100 already. So yeah, so with how much time? Only 10? Okay. Maybe I'll just quickly mention one more word, and I wasn't sure if I'll be able to cover this. Zoom share. Okay, it's showing. Okay, fine. Yeah. So this one is something we published at CVPR last year. So all rivers run to the sea, private learning with asymmetric flows. So the key problem setting was this, which I was mentioning in the beginning. So we have a user server setting. I want to have some private information, private computation. I want to utilize the cloud resources as well. So how do I kind of remain as private as possible while still able to utilize the infrastructure in public environments? So, and yeah, in these settings, typically utility, complexity, privacy, they are pulling at each other. So there are various trade-offs that one can explore. There were different prior methods. For example, you can privatize your data. You add some DP noise to your data, then release it. Then you don't have to worry. There are like fixed privacy guarantees. But then the issue is that although there is provable guarantee, there is a severe accuracy drop. Then there are crypto-based ML where you take your data, you encrypt your data, and then the computations are also designed such that they can work directly on the encrypted data. And then once you get the results on the encrypted data, you decrypt the results. So that process, it provides strong protection, but it has a very high complexity. Then there are all these hardware secure enclaves, which first developed, I think, by Intel, SGX. So they provide a secure environment. They claim that whatever you do inside the environment is private, even with respect to the operating system in that machine. So it's really, really private. But the issue is that although it provides hardware security, it has long running times and also limited compute and memory. So we leverage both differential privacy as well as trusted hardware, and we overcome the accuracy drop, naive differential privacy as well as long running times of the trusted execution environment. So let me directly go into the method. Yeah, so so this is kind of our proposed method. So all the things that are there in red, we are doing it in a private environment. So maybe my local GPU, or maybe my trusted secure enclave. Everything that is in black, it is kind of exchanged with the outer world or the public cloud. So what I'm doing here is that whatever image I have, I pass it through some feature extractor, and then I do some decomposition on my data set itself. So there is a main component, which is the low rank component, and then there is this residual component, which I want to share with the server. But before sharing, we are going to add some noise, and then after that DP noise also, we are going to do some quantization. So the idea is that I am doing a decomposition of my intermediate activations. A part of it is only there inside my private environment. So using that, I'm going to train this part of my training. And the residual component, it doesn't have much privacy, much sensitive information. That is shared with the public cloud. So that's why there is this asymmetric flow. The flow inside my private environment is kind of capturing most of the sensitive data, and the one that I'm sharing outside, it has less sensitive data. Even on top of that, I'm applying differential privacy and some quantization to further reduce the privacy leakage. And even in the backward propagation, there is no leakage. For details, I can discuss it offline. Okay, so some empirical results. For example, let's say I consider ResNet 18 on ImageNet. So MN is the case where only this pipeline exists. There's no secondary pipeline. Only the primary pipeline is there. So it's completely private. There's no data exchanged at all with the server. So for MN, I have, let's say, an accuracy of 64 point something%. Then I'm trying to utilize the resource of the server. But then I'm using some differential privacy on my residual component with epsilon equal to 1. So already we have got an improvement of almost like 2%. As I add lesser noise, so which is less private, I'm going to have better and better performance. And this is the part where it's the original model. No asymmetric flow, nothing. So we see that we are able to provide a trade-off so people can decide what epsilon they want to consider when they are sharing these intermediate activations in a decomposed way with the server. So lightweight model, it achieves good accuracy, but still residuals are useful. So what I have not told in this process is that because of this residual type of algorithm, I am able to train much smaller model locally. So smaller model locally, lesser computation, lesser memory and everything, and still I am able to get such a good performance of roughly 64% with ResNet 18 on ImageNet. And another important aspect is I'm sharing some information with the public, right? So although it has DP guarantees, there's no formal connection with how much DP guarantee you provide and whether it is robust to model inversion attacks. So you have to go and check whether you are robust to model inversion attack or not experimentally. So that also we did, which is shown in this image. So these are the original training samples. Using model inversion attack on the intermediate stuff shared with the outside world, we are able to reconstruct some images to some fidelity, like this one looks something like this, but others are more or less you cannot say much. Maybe this also you can say something. But then if we add that DP noise and do the quantization, we see that hardly you can do anything about it. Like the reconstructed samples, they have hardly anything in them that you can see and decide that whether it was the original image or not. So what I have shown here is that locally you are able to provide a smaller computation, and where whatever information you share with the cloud, that also is kind of protected. So yeah, with this I think it's a good time to conclude my talk.
Thank you, Professor, for accepting our request and delivering such an interesting talk. Are there more questions from the audience? Thank you everyone for attending. We have arranged refreshments in the coffee huts. Thank you, Professor.
Sure, thank you. Thanks for coming. Thank you.